This is day 2 of review of integration. So one of the major rules that we used yesterday was just the power rule. So remember, if you're integrating x, the only thing that happens is the power goes up by 1, you divide by the new power, and then you add your constant of integration. But if there's things that are multiplied, divide, or any type of composition functions, we have to do what's called a U substitution. So things that are a composition function, you see right here, I really have an entire function inside of x to the 5th. That's a composition function. There's something inside of it. Something like sine of 3x. That is not just x in there. That is a composition function. The square root of 3x plus 2. This is a composition function because it's not just x on the inside. So when it is a composition function or there's a multiplication or division that you can't get rid of, one thing you can try is U substitution. When you do U substitution, you're usually going to let the U be things under powers in the denominator, inside of trig functions, inside of radicals. Those are the places you're going to look for what we're going to make U. Now, once you claim a U, you have to look to make sure its derivative is somewhere there to cancel. So on this first one, I would let U equal this inside. Since that is x to the 1st power, I don't need any of my x's to cancel. So whenever we take our U, that means we're going to have to change our entire integral over to u's. So instead of dx, I'm now going to have du, which is the derivative of u, which will be 3 dx. Solving for dx, that's the same thing as du over 3. So this under here in the radical is u. The dx is going to become du, and then divided by 3, we're going to pull that out. We integrate this just with the power rule. So we're going to go up to the 6th power, so u to the 6th, divide by the 6th power, 18th, plus c. But if our original integral started with x's, we need to make sure it ends in x's. So we go back and we resubstitute what u was. And we're done. Notice if that you take the derivative of the inside, you do in fact get what was inside the integral back. So if I took the derivative of 1/18 3x minus 4 to the 6th plus c, if we take the derivative, of course, plus c goes away. Power rule will have 6 over 18 3x minus 4 to the 5th times 3 from the chain rule. And you see that's going to leave us with exactly what was inside of the integral. Okay, so you can always check them. And then the next one, let's see again. Here I have a product. And products, we don't have a product rule for integrals, so we're going to try to either simplify or do a U substitution. This is to the 5th power. I do not want to multiply that out 5 times. So that means there's probably a U substitution that will help. So if I look at the inside of this power and I let that be my U, notice that the power is x cubed. So we're looking for the derivative or the 1 degree less power to be out front or somewhere. And if I take the derivative of this, I'm going to have x squared, and you can see that it is right here to cancel. So let's see, u, x cubed plus 4. Take our derivative with respect to u. Solve for dx. So inside this integral, this right here is going to become u to the 5th. We had 6x squared, but now we're going to divide by 3x squared. So that's going to leave us with 2, and I'm going to go ahead and just pull that 2 out. And then we just have the du. Integrate this. we go up 1, divide by the new power, plus c. And remember, if our integral starts in x's, we need to make sure it ends in x's. And again, if you take your derivative, you'll get the thing back that's inside of there. So if you look, if I took the power rule here, I would have 6/3 x cubed plus 4 to the 5th, multiplied it by 3x squared, the derivative of the inside. And you can see we are left with this 6x squared out in front. Number 3, we have a division. And there's no way to mathematically simplify that division. I cannot factor, I cannot cancel because I can't factor anything. I can't do long division because the degree of the top is less than the bottom. So there's nothing else to do but let there be a u. So if we let u equal the bottom, the power is 2. And notice the derivative, x to the first power, is hanging out to be canceled. So here du would be 2x dx. So then, of course, our 2x would cancel, and we're left with the integral of 1 over u du. And that, of course, is the natural log of the absolute value of u plus c, and then, of course, resubstituting. Now, here, the absolute values are absolutely not necessary because x squared is going to be positive in the reals. We add 1, it's still going to be positive, so it's going to be in the correct domain. A lot of times we do not write the absolute values for natural log and just assume that it's in the correct domain. All right, 4. It doesn't really look like there's a product or anything involved or a division, but what we have here is a composition. It's not just x in there. So you're going to have to let u equal inside the argument. Take the derivative. Notice, since it was x to the first power, we do not need any x's out in front to cancel. So we're integrating secant u du. The integral of secant is natural log secant theta plus tangent theta. So secant u plus tangent u plus c. And again, those are the ones you have to memorize. People do forget them. I do all the time too. I have to kind of think about them. Now we just have some trig ones. So let's see. If I let u be tangent, then its derivative is in fact secant squared. So that will immediately cancel. So here we'd have the integral. And instead of tangent, we're going to write u. Our secant squareds cancel. We have a du. We have some choices. We can choose to change the endpoints of integration or not. I'm going to go ahead and do it this time. So tangent of 0 is 0. Tangent of pi over 4 is 1. So this is going to give us 1/2 u squared from 0 to 1. Since we changed the limits of integration, we do not need to resubstitute back, and we get 1/2. Now, if we didn't change the limits of integration, we would have had x is equal to 0, x is equal to pi 4th, and then we integrate u. When we integrate that, we would 1/2 u squared, and again, this would be x equals 0, x equals pi 4th. But remember, u is really tangent squared, so this would be 1/2 tangent squared x 0 to pi 4th. Tangent of pi 4th is 1, so that would be 1/2. Tangent of 0 is 0, so we get exactly the same thing. Six, again, we have a division we have to clean up. So if we let u equal the cosine of 2 theta, which is kind of not the whole denominator. You do not want to make it cosine of 3 theta. So this is not right. If we said cosine of 3, cosine cubed of 2 theta. Oops, let me write that down there. It's getting cut off. So if I said this is not right. U cannot equal cosine of 3 2 theta, because if we did our du here, we would have a power rule, then a chain rule, and then another chain rule. And you see I don't have a cosine of 2 theta on top to cancel. So you're only going to let it be the trig function without the power. So then your u, the derivative of cosine, is minus sine with the chain rule. So out in front, we're going to have a negative 1/2. And this would be 1 over u cubed, so u to the negative 3. Cosine of 0 is 1. Cosine of 2 times pi over 6 is the same thing as cosine of pi over 3, which is 1/2. Integrating this. So let's see, integrate, you add 1. I'm going to divide by the new power. So then we'll have 1/2 to the negative 2 minus 1 squared. So this would be 1/4. 1/2 to the negative 2 would be 2 squared, which is 4. So 3/4. All right, so looking at 7. If I think about a u substitution, the u would be the entire denominator, and it would not cancel the top. So that doesn't work. The only thing I can think of doing is factoring that denominator, so let's go ahead and do that. Now we have it written as kind of a composition function instead of just it factored out. So here, if we let u equal the inside right here, then our du is going to equal dx. So this would be the same thing as 5 times u to the negative 2 du, which would be negative 5 u to the negative 1. And then, of course, resubstituting back. Eight. A couple different ways we can approach 8. One thing we can notice right away is that we can technically simplify the natural log of x cubed. That's the same thing as, because remember, powers can come down in front. That's the same thing as 3 natural log of x. So if we had noticed that, this is the same thing as 1/3 the integral of 1 over x natural log of x dx. And notice here I do have a product, and it's in the denominator, and I do not know how to integrate natural log. So it must be the u. So if we let u equal the natural log of x, so then du would be 1 over x dx, and then notice that the x on bottom is going to cancel with this new x. So we're going to be left with 1/3 the integral of 1 over u du. And of course, the integral of 1 over u du is the natural log. So we'll have 1/3 the natural log of u. But remember, the natural log of u is the natural log of x plus c. You also could not have noticed that, and you could have went ahead and said, oh, I'm just going to let u equal the natural log of x cubed. And when you went ahead and did this derivative, it would completely work out. Okay, so it does exactly the same thing. You would have just had a chain rule involved in there. 9, everybody's integral that they love to forget. If we're integrating 2 to the x, remember, its integral is 2 to the x divided by the natural log of the base. Okay, but the problem here is this is not just x. It's really composed with another function. So you're going to let u equal that. And you can see that will immediately cancel the cosine. So this would be the integral of 2u du. So that would be 2 to the u divided by natural log of 2 plus c. Okay, 10. Same thing, I've got a product. Products are not a rule for integrals. There's no way I could simplify that. So I've got to do a u substitution. The only thing I can think of is u being the denominator inside the radical. So if I do that, u would be equal to x minus 3. So then du would equal dx. Now, if I do that, then I'm going to integrate, I'm going to the integral of x square root of u and then just du. So immediately this should make you a little nervous. You can't have x's and u's. That x didn't cancel. And a lot of times when we do a u substitution, we're looking for the derivative to cancel. That didn't happen here. But we can notice here that if I go back to my original substitution, we know that x is the same thing as u plus 3. So that can go right here. So this is really the integral of u plus 3 square root of u du. We got a product, so let's simplify it. Integrate. 3 halves will go to the 5 halves with a 2/5 out in front, and u was the x minus 3. So 5, I got something to the 5th power and then a division. Now I really don't want to multiply something out to the 5th power, so I really hope that's our u. So that's what I'm going to try. So then our du, let's see, that's really x to the 1/2. So this would be 1/2 x to the negative 1/2 dx. So that's really du is equal to dx over 2 square root of x. So 2 square root of x, du is equal to dx. So you can now see that this x is going to be on top. It's going to cancel this x out on the bottom, and I'm going to be left with 2 u to the 5th. And of course that goes up to the 6th power with a 1/6 out in front. And resubstitute. So remember here I'm really doing a u substitution being 3x. du would equal 3 dx. So out in front we're going to have a 1/3. Remember, cotangent is really cosine over sine. So you're doing a u substitution with the sine. So you'll have the natural log of sine 3x plus c. Now, we can't integrate the absolute value because there's a sharp term. We can break it up into individual areas. We can remove the absolute value. I'm going to break it up and just graph it and kind of look at the areas. So let's see if I do the absolute value. It looks like this. So if I'm going from -2, it's going to go up here to 2. And this way over here, if it's going to 4, it's going to go up to 4. Because remember, our y is the absolute value of x. So the area of this triangle is going to be, let's see, 2 times 2, which is 4, and half of that is 2. And this right here is 4 times 4, and half of that is, 4 times 4 is 16, half would be 8. So this area is 10. This one, this is telling us y is equal to the square root of 4 minus x squared. So that we know that y squared is equal to 4 minus x squared. And this we know is a circle centered at the origin with radius 2. But we're only keeping the top part of the circle, so we're really only keeping this part. So remember, the area of a circle is 1/2 the radius squared. The radius is 2. So 4, but I'm only using half the circle, so I have to multiply it by a half again, and this area is 1. And finally, a little bit of review of trigonometry, because we're going to unfortunately need a lot of trig this year. So everybody does it a little bit differently. A lot of people do right triangle trig. I know that is one thing that Dr. Johnson really likes. So if this was 30 degrees and this was 60 degrees, and let's see, this would be 2 root 3 and 1. And then the other one, a special triangle, is 45, 45, 90, which would be 1, 1, root 2. One way I have to memorize this, because I don't usually use the triangles, but remember, the smallest side is going to be opposite the smallest angle. So that's why I had to stop and think about it. I tried to put this 1 because it would be a unit circle, so this would be 1, but it's really 2 on the triangle. And let's see, 30 is the smallest angle, 60 is the next smallest, 90 is the biggest, so it has the biggest side. And same thing here, 45 and 45 have the same side, so 1, 1, and this one has to be root 2. Other people, you think about the unit circle, so remember this right here would be 1 and 0. Remember the x coordinate is cosine, the y coordinate is sine, so that would be cosine of that angle, and then sine of that angle. So this first one right here is pi over 6, or 30 degrees, and that is always going to be root 3 over 2 and 1/2. So you're going to do the cosine of pi over 6, or the cosine of 30, and cosine is adjacent over hypotenuse. And then the sine of 30 would be opposite over hypotenuse. And I meant to write 1/2. I don't know why I didn't. So the next one would be your pi over 4 and 45 degrees. This one gives you root 2 over 2 and root 2 over 2. The next one is pi over 3, or 60 degrees. This gives you 1/2 root 3 over 2, 0, 1, and of course that's your 90 degrees, or pi over 2. So if you know your right triangle special triangles, or you know the first quadrant of the unit circle, then you can do any trig evaluation. Remember that all students take calculus. This tells you which ones are positive. So all trig functions are positive here. Sine and its reciprocal are positive here. Think about that. Sine is y. It's above the x-axis, so it's positive. Cosine is x. It's to the left of the y-axis, so it wouldn't be. Here, tangent and its reciprocal, cotangent, are positive. And think about that. In the third quadrant, both x and y are going to be negative, so both sine and cosine are going to be negative, which means the ratio for tangent is going to be positive. And over here, cosine and all of its friends are going to be positive. So knowing what the right one, the reference angle value is in quadrant 1, then you can figure out the plus or minus sign by what quadrant it's in. So reference angles are your angles in the first quadrant for your trig function, angles in first quadrant. So our most famous reference angles are 30, 45, 60, but of course 10 could be a reference angle. It's in the first quadrant. It's just not one of the special ones. Coterminal angles are angles that terminate at the same place. So unlike Cartesian coordinates, x, y, where every point is unique, polar's not that way, or anything with trig, because if I'm talking about theta equaling 10 degrees, that's the same thing as theta equaling 370, because everything's very cyclic in trig. Cosine of pi over 3. So pi over 3 is the same thing as 60 degrees, and cosine then would be, so here's 60 degrees, cosine would be adjacent over hypotenuse. One thing I really love about radians is that you immediately know its reference angle is pi over 4. Sine of pi over 4 is root 2 over 2. And where is 3 pi over 4? So here's pi halves. Here's pi. 2 pi. So let's see, 3 pi over 4 is not quite a pi, so it's going to be right here. That's the second quadrant, and sine is positive in the second quadrant. Sine of 11 pi over 6, its reference angle is going to be pi over 6. Sine of pi over 6 is the same thing as sine of 30, so 1/2. But 11 pi over 6 is almost 2 pi. It's over in the fourth quadrant, so it gets a negative. Cosine of 3 pi over 2. Directly down on the y-axis is 0. Cosecant of 4 pi over 3 is 1 over sine of 4 pi over 3. Sine of 4 pi over 3 is the same thing as sine of pi over 3. That's its reference angle, which is root 3 over 2. So this would be 2 over root 3. Cotangent of 5 pi over 6, 1 over root 3. Secant would be 1 over cosine. Its reference angle is pi over 6. So root 3 over 2, but reciprocal, and it's in the second quadrant, so it's negative. Tangent of 2 pi over 3. And it's in the second quadrant, so it's negative. All right, so now the arc trigs. You're going to do the exact opposite of what you did before. So this time, this right here is your ratio of the sides of the triangle. And what you want to give back is the angle. But we want answers that are going to be unique. So if we're talking about arc sine, we only want our answers between negative pi halves and pi halves. That's the same thing for arc tangent. The reason why, think about this, all students take calculus, all of them are positive here, and sine and tangent are negative here. So between these two, I'm going to get the entire range of those values because I have the positive values and the negative values. That would not work if I chose to do first and second quadrant because this is positive here and positive here. I could have chose that for tangent, but they did not. The default is the first and the fourth quadrant for sine and tangent. For arc cosine, its default is 0 to pi, and its reason is because it's positive here and negative here, so I get the full range. So when I take, say, arc sine of 1/2, I'm looking for the angles whose sine is 1/2. So that would be opposite over hypotenuse, so it's going to have to do with 30, which would be pi over 3. No, pi over 6, sorry. Pi over 6. And then this would be positive pi over 6 because this is positive on the inside. Arc sine of root 3 over 2, negative root 3 over 2. So first thing, the arc sine of root 3 over 2 is going to be pi over 3. But since this is negative, it needs to be negative pi over 3. This is the same thing as the arc tangent, which would be pi sixth. And arctangent of 5 pi over 4, this was totally a typo. It should not say 5 pi over 4. Let's say 1. Actually, let's say negative 1. So negative pi over 4. Now, if we have an arc nestled inside of a trig. Okay, I did some typos over here when I was typing this up, so I need to fix this. This was supposed to say the tangent of the arc sine. Let's do the tangent of the arc sine, and we're going to say of square root of 3 over 2. So we're looking for the angle whose sine is root 3 over 2. That's whose angle it is. We want the tangent of that angle. So Pythagorean theorem. So this would be 1. So the value of the tangent would be root 3. So same thing here. The angle whose sine is 1/2, so 1 over 2. Completing the square, so 4 minus 1 is root 3. And then we want the sine of that. Well, the sine of that is also going to be 1/2. But that makes sense because the sine of the arc sine should cancel itself out. And then again, I just somehow wrote these backwards. So tangent arc sine of x, sine arc cosine of x. So here, the arc sine, that's whose angle's sine is x. Pythagorean, that would tell us the tangent is x over the square root of 1 minus x squared. My cosine is x. So then my sine would be the square root of 1 minus x squared.